Okay, good evening. Let's start our today's session, the week 6 doubt clearing session for aluminum based alloys and metal matrix composites. I am Ananya Nath. I am a PhD student in the Department of Mechanical Engineering at IIT Delhi. So in this week, the topic was mostly recovery and recrystallization. So we'll be talking about the recovery and recrystallization in this session. Also, we'll be covering the last semester or last year question from week 6 quiz, and also we'll be discuss about the current semester quizzes of last 2 weeks. So let's start today's session. If you have any doubt, you can ask me. Otherwise, I'll start with my PPT.
No, ma'am. Can we run through everything once?
Sorry?
No, ma'am. Everything is fine as of now. Can we run through everything once?
Okay, no problem. So in last week, we were talking about the strain hardening of non-heat treatable alloys. Just a recap. So there we got to know about how we were stopping the dislocation motion by introducing a lot more dislocations. So there were jogs and kings were introduced because of the interaction between different types of dislocations. Then there was this cross slip and climb. So cross slip and climb was needed for us for the recovery part, but in today's or in this week session we'll see the cross slip is something that we don't want for the recrystallization part. So cross slip was just movement of the dislocation from one plane to another plane if the planes are in the direction of their slip direction, and those are perpendicular for some case parallel for screw dislocation, and perpendicular for the climb means edge dislocation. Then we talked about the cell structures. So dislocations were arranged by themselves in such a manner that they were making some cellular structures, like they are kind of making some loops, and loops have a definite kind of width and length in which they are looking like some sails. So this cellular substructure formation is very important for our this week lecture, because there you'll see how these things are evolving to give rise to the new grains and nucleation growth, these things. So in last week 5, so in week 5 the last two lectures were not covered in last session. So let's start with that. So first was recovery. So recovery means if we have introduced a lot of hardening in a material, so now we want to remove some hardness, or the material is over aged due to the natural aging condition. So we want to remove the hardness. So we have to introduce some, or we have to revert back some ductility again inside the material. So due to which we were going through the recovery. And recrystallization means giving rise to some new grains which are strain free. So in last class we have talked about strain free grains. So what do you mean by strain free grains? Strain free means there are no dislocations present as such inside that particular grain. That will be called as strain free grains. The grain will have a definite type of crystallization, means the unit cells and the lattices are arranged in a particular manner in a particular direction, and um, that particular grain is located somewhere inside the material, is having some particular crystallization but doesn't contain any dislocation inside it. So this is how we were taught. So for recovery, uh, so we have introduced a lot of cold working inside the material for the recovery part. So cold work will introduce a lot of dislocations inside the material. which are new dislocations. So that dislocations can interact with the previously grown dislocation or old dislocation, or also they can interact themselves also, because the number of dislocation is so high, like 10 to the power 5, 10 to the power 6 numbers. So due to which it may happen that the opposite sign dislocations meet and make a continuous line. So again there will be no dislocations present after that. Or if they are of same sign, then they can just get arranged in such a manner that would be a low angle uh, or low energy configuration for them, because all the type of solutes and dislocations, their motive is to get arranged in a low energy configuration, so that they don't need to spend much energy on making themselves arranged, or being at a stabilized or equilibrium position. So yeah, they will get arranged in a low angle for edge, a twist angle for screw configuration, which is nothing but which denotes the low energy configuration. So then if they are arranged, so they will not move further. So if they are not moving, means there is no dislocation movement inside the material. So no dislocation movement means uh, that is strain hardened. So that was one thing. Then the dislocations, okay, arranged at a higher temperature, energy of the system decreases. So obviously if they are getting arranged, so the system is not anymore active in that sense. Adjacent portion will be free of dislocation and strain. Again, if the dislocations have arranged themselves in a particular manner, whether it can be high angle or high energy configuration or low energy configuration, but if they have arranged themselves, means they have gathered in a particular position, in a particular space or place. So other than that place or adjacent to that portion, other places or other lattices and crystals will be dislocation free. So that can be considered as a new grain, which can be called as strain free grain, which is our main motive to get from the material after recovery and recrystallization. So recrystallization is replacement of deformed crystals of high dislocation density by strain free crystals. So before, when there were a few number of solute atoms and few number of dislocations, there were they were just moving, like the dislocation is moving, the solid atoms are trying to catch this dislocations and pin down them. But then we have played like we have increased the number of dislocations, so that the number is so high that they cannot move further, they will start interacting with themselves only. So that was our motive. So next is mm, huh, the effect on recrystallization of various process parameters. So one is degree of prior deformation. So recovery is okay. We have done the cold working, and this is why uh, like we are getting that recovery part. But after cold working also, something is going on inside the material, because in cold working the number of dislocations will be high, increased. Dislocation तो बढ़ गया. But now what to do? What is happening inside the material, so that we are getting that recrystallized grain? So that is what we will be discussing here. First is degree of prior deformation. A little cold working is needed to start the recrystallization. So it also happens in heat treatment processes, in various manufacturing processes also. We often go for recrystallization because we want some new grains to form inside it, because the new grains which will be forming will be having some lower dimensions, means their size will be lesser. So less grain size means some hardening, some strengthening, which is always needed. So there also we sometimes want recrystallization. But for recrystallization, if we have some prior deformation, it will help us to get the new grains easily. So higher the deformation, higher will be the stored energy, which means like a lot of dislocations has gathered, and high driving force to get the new strain free grains and their growth, less recrystallization temperature and finer grains. So after deformation also we need to have some temperature and time things. So for that, for few time interval or for few time, we'll keep the material at a higher temperature, which is called the recrystallization temperature. Every material does have a recrystallization temperature at which the material starts forming new strain free grains inside them. So that's one thing. Next is the initial grain size. So if the grain size is very big inside the material and we are doing the recrystallization, so obviously the grain size will be lowered down. The new strain free grains will have lower dimension or size, but obviously if it's already finer, the grains, the initial grains, it will help us to get more fine or finer grains. That is one thing. Also, finer grain size will need that is grain, sorry, there is a typo, more. So finer grain size means the grain boundaries are more, because each grain is separated by the grain boundary. So each grains are having some grain boundary. So if the grains are finer, means smaller in size, so obviously the number of grain boundaries are more. So in that case, higher recrystallization rate and lower will be the crystallization temperature, and the grain will be finer, better finer. So the temperature of cold working is also important, because it doesn't mean cold working means we'll be doing at this, will be carrying out this cold working at a cold temperature. No, it can be at room temperature, it can be at elevated temperature also, but not equal or more than recrystallization temperature. The cold working may take place at more than room temperature also, but not recrystallization temperature. It should be many less than the recrystallization temperature. So less the temperature of the cold working, more strain energy, more strain, that means so higher driving force, so less recrystallization temperature. So we want the deformations to be taken place inside the material more and more, because deformation is something which will give rise to more and more number of dislocations. So that is our main motive. Next is the temperature of the recrystallization. So the recrystallization rate depends upon the temperature exponentially, because there is one formula in which you'll see the temperature is a function of this, uh, recrystallization rate is a function of the temperature, but it's having a exponential relation. So effect of solute atoms and the second phase. So we are talking about the dislocation, density, the number of dislocation and these things. But there are the solute atoms and the precipitates also have formed. So they are present inside the material. So they should have some contribution in this process as well. They can interrupt the process, or they can just help in this process as well. So it's like the solute atoms and the second phase particles hinder the motion of the dislocation at the grain boundaries. Obviously, grain boundaries are the high energy zones in which the dislocations, if they are moving, they will get stopped at the grain boundaries. Also, For solute atoms, the solute atoms are finding some adjacent free or vacant places in which they can jump. So for them also, it's important to have a vacant place adjacent to them. But if, as I have shown in the last class, what do you mean by grains? So for jumping into different grain, they need more energy. So their motion also gets stopped at the grain boundary sometime if they don't have sufficient amount of activation energy to jump into the next vacant place. So if there are solute atoms present or the second phase present inside the material, so they will always hinder the motion of the dislocation at grain boundaries because both of them are now getting stopped at the grain boundaries. So grain boundary move, uh, yeah, so that movement is being hindered, stopped. Recrystallization rate decreases with the increasing recrystallization temperature. So it's not like that it's not like if you are increasing the temperature it will be good for the material. There is a relation, there is always a dependency and some relationship between each parameter. So yeah, cold working is also needed at some elevated temperature, or sometimes it's needed at room temperature, below room temperature. But it again, it's not like if you keep on decreasing the temperature it will always help. No, there is certain range of temperature in which you have to work through. So the next one is the grain growth. So after the dislocation movement is hindered, there will be some mechanism by which new grains will be formed which are now strain free, means which do not have any dislocations inside them. Now this grain needs to grow. Our motive is not to only give rise to some new grains, also the growth of the grain is important. So more average grain size, less number of grains, obviously. Driving force for this is the reduction in surface energy associated with grain boundaries due to grain growth. So the grain will try to grow if they experience a little bit of temperature less than 5-degree misalignment, same grain. That means we saw in the last class that if there are two grains, means this both the grains have their lattice or crystallinity in a particular direction. That is why they are being accepted or they have been introduced as a separate grains. So if this separation, this thing is less than 5 degree, na, then it will be called as same grain. But if the misalignment in between two grain is more than 5 degree, means they will be considered as separate grains. This is one important thing. Then there were some technique like DSC by which you can measure the heat that is being released by the material during this recovery and recrystallization.
Excuse me, ma'am.
Yes.
Ma'am, you just said that less than 5 degrees, we can also call it low angle boundary.
Okay, no, no, low angle boundary is something related to the dislocation.
Um, I'm a bit confused like about this. I have heard something that between 2 to 5 degrees of misorientation could be low angle boundary, and more than 15 it would be higher angle boundary.
That is for dislocations. Okay, I am talking about the grains. Okay, this is the grain. In grain, there are the lattices. Inside the lattice, there is the dislocation. I am not talking about dislocations. Dislocations pile up. Dislocations get piled up and they make the new grains. In that case, this 2 to 5 degree, more than 15 degree, these things are considered. because low angle and high angle is something related to the dislocations. I am talking about the normal grains which are present inside every material. So if the grains are having less than 5 degree, they will be observed as same grains. If you are seeing under the microscope, then also you will see you cannot distinguish two grains if there is less than 5 degree misalignment.
Got it, ma'am. Understood.
Yes, ma'am, because like even if we say in the case of twins, so like twins are like that only, na? Like means even in twins some misalignment is there, but that is within the same grain only.
Yes. So twins look like this under microscope. They will have same type of alignment, but they will be colored with different colors, and you'll recognize easily where are the twins. So yeah, next was DSC. So DSC is differential scanning calorimetry, which is a machine. I'm not going into the deep of the working of this machine. It's typically used to measure how much heat it's releasing, or how much heat it's taking to get that recovery and request or the recovery done. So there were some graphs like this, which were denoting either endothermic or exothermic reaction is taking place. So next topic was polygonization. Polygonization means if there are some dislocations, if this is the grain boundary, if there are opposite sign dislocation, they will meet and make a continuous line. There will be no dislocations anymore. But if they are of same sign, they will try to get arranged in a low energy configuration. This is what they are calling it as low angle boundaries. If they are aligned like this and they are aligned like this, they can make a separate grain, which will be taught in the upcoming lectures. Like in this week 6 lectures only, you have already seen those videos. So that is the thing. So they are making some, they are been gathered at the boundaries, at the grain boundaries, with a low energy configuration. That is called the low angle boundaries. So that is polygonization. So after polygonization or in polygonization, so the recrystallization is done. So during polygonization, there were this grain boundary bulging. I'll be talking about that. So due to that, the grain growth and nucleation, these things happen. But if we keep the material for longer time at that little temperature, there can be abnormal grain growth after nucleation that can hamper the material quality that I am wanting after the decrystallization. So that will be called as secondary decrystallization. And the reason for or secondary decrystallization mm, is the time and temperature. So we have to select the time and temperature very carefully. Otherwise, as I said, there will be a range of time and temperature, also a range of cold working. If you are going beyond that, there will be secondary recrystallization or some abnormal grain growth or something that we don't want. And also a temperature at which this 50% volume of the material has recrystallized in 1 hour. This thing is called as recrystallization temperature, but it also depends upon the material, how much time it's taking. So this, so there is a relation between the time and temperature. So the temperature the material is taking, that will be called as recrystallization temperature. But it may happen that if you have somehow changed the cold working, that specific material will take lesser or more time to get recrystallized. So even if the definition of the recrystallization temperature is this, that a temperature at which 50% volume of the material has recrystallized in 1 hour, but it may get changed according to the cold working, and some other environmental interference. Next is this picture that I got. So as I said, the deformation. So this is the prior deformation which is needed for the material to start the recrystallization. After that, as will increase the deformation, the grain size is decreasing, right? Which is needed. But the curve doesn't look like this. It will keep on decreasing only. After some time it will get again increased. So this is why I was telling there is always a range in which you have to work, otherwise it will act abnormally. The next picture I have is this recrystallized grain size and the amount of cold work, which is similar, but here you may find some different temperature for different types of alloys and MMCs. Here is the list. For different alloys, we are getting different points. For MMC of same material, we are again getting different points. So yeah, for the solid atom interference, environmental interference, and the cold working, all depending upon all the process parameter and their interaction between each other, these things are happening. Some different types of results we are getting. So next is this one. Okay, it's showing us a graph between the annealing time and the grain size. It's related to the previous lecture, but I found this graph really interesting so that you can get some idea about it. Uh, the next is this recrystallization fraction, means how much is recrystallized. That we said now 50% volume will be recrystallized. So this is what we are getting. For different temperature, we are getting different types of graphs depending upon the time and the temperature. The recrystallization fraction is changing. It's for different alloys. The three graphs. Then is the Arrhenius equation. So in week 6 lecture 1, we have taught about the grain orientation or grain rotation, and then the bulging, and then the recrystallization percentage, the dependency of recrystallization with the time, with different temperature, and then we were taught about the Arrhenius equation. So Arrhenius equation is something like k equal to a into e to the power minus ea by rt. The same formula is applicable here also, where the 1 by in place of rate constant k, we have used the rate at which 50% of the structure is recrystallized, which is denoted by 1 by tau. A is the some constant or factor, and then Q is the EA is replaced by Q, which is the activation energy for recrystallization. R is the gas constant and T is the absolute temperature. So this was one thing. Then comes the dynamic recrystallization. So I'll come to the bulging and the rotation part. Before that, just let me tell you one thing. In the case of strain aging also, there were the dynamic strain aging. Not similar thing, absolutely opposite thing. But for example, I'm saying for strain aging also, we were doing some aging, and due to which we were getting some more hardness. But when at the time of deformation, we were getting some more hardness. The yield point reappear. That was called as dynamic strain aging. Similarly, for recrystallization, after recovery, we keep the material at a particular elevated temperature for some times. But at the time of recovery or at the time of deformation only, if this is happening, the recrystallization or new strain free grain formation is happening, that will be called as dynamic recrystallization. So from dynamic recrystallization, the things are pretty easy, but what you need to do is visualize the things. Otherwise you'll feel a lot of difficulty in understanding the things, because all the things are very similar to each other, very interrelated or correlated. So the classification also, you'll see the discontinuous, continuous, and geometric dynamics recrystallization. The difference is not that much, but yeah, there are some difference between these two processes. So let's see that. So first is DDRX, means dynamic uh, discontinuous dynamic recrystallization. So what happens is, uh, it's called discontinuous. So the result will be inhomogeneous, means in CDRX as it's continuous, the new strain free grain formation is homogeneous. In case of CDRX, continuous dynamic recrystallization. But for discontinuous, it's not that much homogeneous, but it's as simple like the normal static crystallization. So for static, what was happening is, after the cold working, when the cold working is done, we were keeping the material at some elevated temperature, and for cold working a lot of dislocation was appeared inside the material, was formed, and due to the higher temperature and for a particular time, the dislocations were arranging themselves in a low energy configuration to get a stabilized form. It's nothing like that. So here in this picture you'll see there are some low angle boundary, high angle boundary, and the initial grain boundary. So for bulging, it's like this was in the initial state, this was the grain boundary, where this was the low and this was the high dislocation zone. Means in the left portion, the density of the dislocation is very high, and in the right portion, the dislocation density is very high, very high. So here it's very low. Sorry. So what will happen if somehow, due to the temperature increase, due to the dislocation movement and other causes, the boundary is bulging here, just a portion of the grain boundary is trying to go and enter into the high energy zone or high dislocation density zone, it will move like this, and as soon as the grain boundary will bulge, the dislocations will start getting arranged themselves very fast, because here the density is very high, although here the density is low. So at the time of bulging they will get arranged themselves very fast. The dislocations present here in this portion will move, will rotate, and will arrange themselves here in this portion, and like that if it continues, it will form a new grain which is smaller in size. Obviously the new grain formation was started with a bulging of a small portion. So this is what been shown in this picture. So for this bulging to happen, two thing is important. One is migration and another thing is rotation. Migration means they are moving somewhere. Rotation means only rotation of the grain. So it may happen, as I said, if normal two grains are having 5% misalignment, they will be considered as same grain. But if it is more than 5%, then there will be two separate grains. So if it's more than 5%, they will try to get arranged in less than 5% state, so that there can be coalescence between two grains, and they can be called as new grain and one grain, that is a low energy configuration for them to get an equilibrium position. So this is one thing. Grain rotation and migration is simple thing, like the dislocations are moving fast as the temperature is increased now, and they are trying to get arranged at a particular position. So this migration and rotation is important for the recrystallization to occur. It was happening in case of static recrystallization, means the normal recrystallization where the temperature was applied. But here for dynamic recrystallization, the temperature is not applied till now. It's happening abnormally, because for us we assume that we'll be getting some dislocations only, but at the end we are getting some recrystallized gain. So this is why it's good for us. Don't have to go for the elevated temperature things now, but still it's an abnormal thing for us, because this is not the right time for them to give rise to this new grains, but it's happening. So for DDRX, it's simple. It's like static recrystallization. The static recrystallization is happening inside the grain due to this bulging, rotation, and movement. These things, and it's also happening due to the low angle. What's it? Low angle boundary or low energy configured dislocation boundaries. And this is why this bulging is not a it's it's not a homogeneous thing. Na, this bulging is a random thing. This bulging may happen in different locations and very randomly. So this is why the spreading of these things, of this new strain free grains, are not homogeneous as much as we can get in case of CDRX. So this is one thing. Now the next important thing is SFE. Okay. So SFE, the stacking fault energy. So we were taught like stacking fault energy should be high for the recovery, but for this recrystallization part, we want low SFE, because for recovery, or not recovery, but at the time of cold working, we wanted the dislocations move very fast to get arranged only. So this is why we wanted the high SFE, but here we want low SFE, because if the SFE is high, then again, or if the stacking fault energy is high, the dislocations will just move randomly and we cannot get that recrystallization, because if the dislocations are moving very freely, it may get introduced in the strain free new grain. It can enter into the strain free new grain. So this is the reason we do not want the SFE to be high in case of uh, recrystallization. When the recrystallization is happening, we want the dislocations to stick into one point. They may get erased by the migration and rotation, because this migration and rotation is taking place with a bunch of dislocation. It's not like one dislocation is moving. Here in recovery, all the dislocations have gathered at one place, and now at the time of recrystallization, they are moving all by themselves with a bunch. So one dislocation is not moving, and we do not want this to happen. So this is why the SFE to be low in case of this thing. There were one important parameter, which is Zener-Hallman parameter Z, which is again, which looks like the Arrhenius equation again. So Z is equal to strain rate e to the power minus Q by RT. Q is the activation energy and R is the gas constant and T is the absolute temperature. So this Zener-Hallman parameter tells us about the type of DDRX which is happening. So type of DDRX means what will be the result after this DDRX. How we'll get like lower Z will denote as, okay, it's not printed. It was having some strain rate. Okay, no problem. So there is one symbol here. So if This equation is telling us that z is directly proportional to eta dot. So this is why if z is high, eta dot will be high. But in that case, low angle boundary dislocation formation will take place. But for lower z, the rate will be lowered. So in that case, twin boundary will be formed. So this is one thing. So remember, DDRX is happening just like the static recrystallization. The only difference is in static, the recrystallization is happening or taking place at higher or elevated temperature. For DDRX, it's taking place at the time of deformation only. So for this case, uh, the driving force, why this is printed like this? This was nice at the time of, okay. The driving force for bulging is the grain boundary, higher dislocation density. So all we know is when the dislocations are moving and trying to get arranged by themselves, they will get arranged at the gain boundaries because that is the low energy configuration for them. And DDRX is dependent upon that low energy configuration dislocations only. They deal with the low energy configuration dislocations because no extracurricular things are happening inside the grain boundaries. The dislocations were normally moving and getting arranged at a low energy configuration. Only that thing is only happening at the time of deformation. So the driving force for this is also like the bulging in the grain boundary, then migration, orientation, those things. Dislocation subtraction may happen obviously if they are of with opposite sign. They may get a continuous line as a result and subtraction will happen. Also, they are arranged at the grain boundaries, so they can be they can get divided into separate grain boundaries. The density may change a little bit, but that's not that much important. But the grain boundary is undergoing some shearing. So what happens is when, so if this is the grain boundary, the dislocations are present like this and they are getting arranged. And if somehow they are making some cell structures like this or like this cell structure is having some another configuration or crystallinity other than this actual grains. If this is the grain and this is the serration, so this is called as serration. So if there is a grain and at the grain boundary the dislocations have gathered, and somehow for their higher density and the cold working things they are getting arranged and making some cell structures, then there will be some lattices present inside the cell structure. So obviously if they are making something, so dislocations are also nothing but the lattices, no, the extra half plane. So the extra half planes are getting arranged, but inside that the extra half planes are extra from one direction, but other direction they are connected with other atoms, na, they are having some lattices. Maybe they are extra at this plane, but in other planes other lattices are present. So obviously they are having some crystallinity and lattice structure inside that particular thing, cell structure, and that cell structure is very different from the actual grain or cell structure, actual lattice structure. So there is an incompatibility between this grains and the cell structures. So this is why there will be some shearing in the grain boundary. The grain boundaries are not very stable at that place. They are having some shearing and serration. Serration is accumulation of the grain of the dislocations, at the grain boundary. So serration also meant thus like the same thing in case of strain hardening also we saw there. The serration was like the solute atoms have pinned down the dislocations by sitting in front of them, and the dislocations cannot move anywhere. Now they are getting gathered at the backside of the solute atoms, and when they are lot in number and they have gained that activation energy, they will again overcome that barrier of the solute. Those things were there. So similar concept here also, serration. So DDRX, it's simple thing. At lower strain rate, the grain boundary migration, sliding and rotation, these things occur because for lower strain rate, for higher strain rate, the dislocations cannot move anyhow. The solute atoms can move due to the higher temperature, the temperature risen due to the higher strain rate, but for lower strain rate, the dislocation, that pile up dislocation or loop of the dislocation or the cell structure of the dislocation can at least move or slide, glide, rotate, migrate, whatever. Next is the serration prevents the migration sliding, because serration means they have gathered at a particular place. So now they cannot slide very easily. They have to move all in a bunch. That's what I was telling. Then adding extra strain gradient means this, it's like the dislocations have gathered. So previously, there were a lot of dislocation. Now they have gathered at a particular place. We were wanting this gathering of dislocation. So we wanted SFE to be high, but now we want SFE to be low so that this gathered dislocation cannot move anywhere. Now they are just trying to glide, slide and rotate to get this cell structure. But when the, as we wanted the SFE to be low, now they are having trouble to even migrate or slide. At that case, in that case, they will feel again some more stress and as a result strain. So these serration are having some different strain, and this grains are having some different strain, and due to this strain difference, there will be some strain gradient, and that strain gradient will give rise to the recrystallization. How? Due to this strain gradient, the dislocations present inside this cell structure will move any one way, like in a E dot 1 side or E2 dot side, and this is how the in between portion of this cell structure will have no dislocation, means strain free grains. So this is how recrystallization is taking place. Next is the grain boundary shearing, as I said, because of the serration. And if this is happening more and more with time, then secondary grain boundary may happen. Also, some secondary recrystallization also may happen if we are doing it for a longer time. But otherwise, secondary grain boundary means the boundary which has uh, been made due to the serration and the migration of the cell structures formed by the dislocation piled up. Bulging occurs. The condition of bulging was given by this equation, and bulging also leads to nucleation, and after nucleation we have to go for the growth. So this was taught up to lecture 2, I think. So in lecture 3 we had been taught about the CDRX. So up to DDRX, if you have any doubt, you may ask. No, fine. We'll go to the CDRX. So remember one thing. I'll show you in one of my pictures also. Yeah, this picture. So I'm just drawing for your reference. So there are unit cells. The unit cell make the lattice. That particular orientation of lattice make a grain, and this is how, due to different orientation in lattice, we get polycrystalline or different grains. And in different grains there are a lot of dislocation. Due to cold working, a lot of dislocation is introduced. Now the dislocations are trying to get arranged in a particular manner so that they can give rise to new grains. So this is the principle. For DDRX, it's more like the dislocations are getting piled up at the grain boundaries. Huh? And in the grain boundaries, they are making some new grains. So there was one theory, like if the crystallinity is having 6 number of edges, then they will try to expand. If they are having 3 or less than 6 number of edges, they also always try to get demolished inside the grain. So this is one theory by the geometry, like they are not stable geometry, they are stable in nature. So this is why. So if the configuration is like this, then it will expand and it will grow. But if the new strain is like this somehow, and if they do not find any favorable condition, they will not be formed very easily. So in DDRX, we are getting new grains out of the previously held grains. So it's like if there are grains, अलग अलग grain है, so in the grain boundary, they are making new grains. And for the next one, which is CDRX, we are having new grains inside the old grains. So these things are different. DDRX is giving rise to new grains at the grain boundary, but CDRX is giving rise to new grain inside the old grains, because there the phenomena depends upon the high, or the phenomena deals with the high angle configuration boundary or high angle boundaries. Here the low angle boundary is formed in the grain boundary, but the high angle boundary may form anywhere, because anyhow that is high energy configuration, that is not stable, but they have rotated in such a way that they cannot be at a equilibrium or low angle position anyhow. So this is how they are making new grains to get stabilized. So CDRX, no nucleation or growth stage as such. There will be some nucleation but no growth state, because obviously we are having new grains inside the old grain. How they can grow inside the grain? If we have we are getting new grains in the grain boundary by bulging or by rotation, sliding, the newborn grain can grow, right? But in CDRX, we are getting new grain inside the old grain. Now the old grain boundary is already defined. How the old grain boundary can grow, the new grain can grow, right? Because they are having that capability. But the old grain cannot grow. They are having some dislocations. So this is why no nucleation or growth phase. Directly we'll get the strain free grains. But as all the grains will have new grains inside it, so the formation of this new strain free grains is very homogeneous in nature. So it also has some advantage. So the next is high angle boundary arrangement. Then nucleation by low to high angle transformation. So already the DDRX has taken place. After the DDRX is done, the grains are having some new grains at their boundary with the low angle configured dislocations. Now this low angle configured dislocations have continued moving instead of sitting in a particular place. So if the cold working is still sustained, so we are still doing the cold working, due to that pressure and stress, the nucleus, the growth is taking place. So this is how, again from low angle configuration, they are rotating and having some high angle configuration. Need some lattice orientation from misalignment. Obviously, in low angle, there can be coalescence. If the degree is less than 5, then it may be counted as one grain. But those things are not applicable here because they are not bothered about that coalescence making new grains. They are just bothered about the rotation, and the rotation will give rise to again misalignment, more and more misalignment. In case of DDRX, the grains were the dislocation cell structures were minimizing the misalignment by rotation, but here they are orienting and having more and more misalignment, so that they cannot revert back into their low energy configuration. So this is why at high angle configuration they are making new cells, new grains. So need high SFE again, because for low SFE they cannot move. So anyhow, if we are getting high SFE, means the SFE, the SF stacking fall width is low. Obviously, the stacking fall width is will be low because we are continuing we have continued doing the cold working. So due to that longer cold working, we'll be having new number of dislocations. We'll again have the high SFE, so more cross slip and more movement of the dislocation is needed here, because obviously we want, or we don't want, but the dislocations need more activation energy to move. This cross slip as high SFE will provide them that activation energy to move further, to get that more and more misalignment. The low energy substructure cell were previously trying to get that coalescence effect, bulging and those things, but here the CDRX do not need these things. High temperature, high rotation and high misalignment, so it will give rise to the high angle grain boundaries of, or high angle dislocation configuration. Dislocations get absorbed in the boundaries. As I said, for low angle configuration, the dislocations get absorbed in the boundaries. But as they have moved further and they have got the more and more misalignment, so now they have formed the high angle one. Finer grains, as dislocations are taking part in more and more orientation होगा ये. It's a mechanical process by which grain refinement is taking place. Obviously, because before this two grain, this is grain 1 and this is grain 2. In case of DDRX, we were having new grain in the joint. But for CDRX, we are having new grain out of the old grain. So obviously grain refinement is taking place, means we are getting finer grains. So next is the triple point. So sir has taught about the triple point, where these dislocations will go and say it will misorient. So triple point means uh, three grains are meeting at one point. It's that simple. That will be called as triple point. You can see in this picture. So this is one grain, this is two grain, this is third grain, and they are meeting at this point. So this will be called as triple point, and they these dislocations move at the triple point because they have option to go in the or towards three grains. They are now present in grain 1, they have reached the grain boundary. So now they have two more options to go, grain 2 or grain 3. Now they will see in normal condition, they will go towards the grain where they will find the low energy configuration. So this is why dislocations motion gets stopped at the triple point. The stress developed inside the grain because of this dilemma in the dislocation movement, whether to go, in which direction to go. So serration, bulging, these things occur because when the energy at this triple point is crossed a particular critical value, there will be some serration inside the dislocation, because inside that grain boundary, because a lot of dislocation has gathered at that place and serration will occur. And serration and bulging will take place along the non-sliding boundaries, because bulging is like two grains are meeting each other, and there one grain has spread their arm in a form of bulge, and at the bulge we are getting new strain free grain. So if the two boundaries are sliding with each other, the bulging may not cannot occur. So this is why bulging will always occur along the non sliding boundaries. The energy diffusion may take place because as at the triple point a lot of dislocation has gathered, now serration have occurred, so energy diffusion may take place. Mantle formation due to the high cold working and accommodating the high strain or dislocation. Mantle means, I have already shown, if this is the grain boundary, first they will gather, then they will form some cell structure. So this is what called as mantle. So mantle formation may take place. Uh, Next is, after bulges, sliding may occur again, because at the time of bulging we don't want any sliding, and if the bulging is, if this is the grain boundary, the bulging has started occurring. Suppose this is its critical size and this is its final size. This is stage 1. The bulging is at stage 1. So as soon as it uh, gets the shape, the critical size, it will continue spreading its arm to get the proper bulge of final state. But beyond or but below the critical size, it may occur at the time of bulging, the sliding has taken place, due to which the bulging could not occur. So this is why for bulging we don't want the sliding. Sliding will be stopped if the critical size is achieved. After that it will bulge, and when the bulging has occurred, it has gained its final shape. After that the sliding may continue doing occurring. So this is one thing. Subgrain formation, yes, due to this serration and these things, the subgrains are forming. Obviously it's at the grain boundary. For CDRX, first DDRX is to be happened or occurred. After that the CDRX may occur. Micro shear bands may form during rotation. So micro shear band, okay, can anybody tell me what is micro shear band? Anyone of you?
Ma'am, like it forms during like what to say, like suppose if some localized deformation has occurred around an inclusion like that.
It's like there. There is a particular
Uh,
orientation. Yes.
is it like when this dislocation substructure is forming at a lower strain, then the misorientation like it has to increase. So at that time, these micro shear bands are formed as the next stage.
Yes, so it's like there are some particular orientation in each grain. There is a particular orientation in the dislocations, which are having some low angle configuration. And now this low angle configuration dislocations are interacting with each other. They are intersecting with each other. And at that intersection point, we are having some micro shear bands which may get some critical size after more and more misorientation and will form some new grains. So it's like that. So here you'll see micro shear bands, which is called MSB. So this is one grain. So this is one grain, not one grain, but one portion which is shown here. So these are having some particular orientation, but at the joint, due to interaction of both the orientation, they are having some high angle boundary because there are some misorientation. Here they were misoriented or they are oriented, but there were some angle between the orientation, but which is having some low angle boundaries. But this two has now these two are low angle. Now they have interacted and given rise to the high angle. It's like that. So these high angle boundaries are now acting as the micro shear bands, which will give rise to new grains. So interaction between this low and high angle boundaries, the high angles are again rotating. So after forming the high angle boundaries, they will again rotate different dislocation network. Yes, as I said, all the dislocations are oriented in a particular manner, but they are having misorientation in between two bands. Dislocation substructure formed by DDRX, DBRX. I have it. Okay. Severe plastic deformation is needed for this because if the plastic deformation is up to the mark, it will not have any dynamic recrystallization. If it has occurred more, a little bit more than the normal uh, percentage, then it will have DDRX. Even after that, we continue doing the cold working, then it will have the CDRX. So this is why severe plastic deformation or cold working is needed here. First, equiax formation of the MSB as shown in the picture. Those are equiax grains. So equiax grains are formed. These are kind of cell structures formed by the dislocations. These are low boundary because they are oriented with each other so that they can have that equilibrium. But they have interacted with each other, intersecting with each other and having high angle boundaries. So these equiax grains are not having the equiax size at the interaction or the junction. This is why we are getting the high angle. So next is the GDRX. So see up to CDRX, I think it's okay. If you have any doubt, you can ask. Otherwise, we'll go to GDRX. Okay. Next is the GDRX. For GDRX, high SFE is needed. Low strain rate deformation formed due to serration. High angle give rise to new grains, and serration is comparable with the grain size. New grains are formed, thinner grains and grain refinement. So what is really happens or happening is there are some grains. In grains, the lattices are oriented at a particular direction. Due to this CDRX, DDRX things, due to CDRX, the grain refinement has already taken place. But again, if we continue doing the cold working, it's getting some reduction in the cross section. So the grains, uh, at first stage, the grains were having the serration due to DDRX, but now they are getting closer due to the deformation and reduction in cross section. Now, when they have come so close to each other that the serrations are touching each other, so then they will form the new strain free grains. Before, the serrations were like this. After cold working, the serrations are like this. But after that, when the cross section reduction is so much that they have come to like this, and if they touch each other, they will form this, this new strain free grains. So this is the concept of GDRX. It's the geometric dynamic recrystallization. So CDRX, GDRX is something occurring because of some mechanical and metallurgical uh, war going inside the lattice in between the different types of dislocations. But GDRX is something which is not happening because of some metallurgical thing, like the dislocations are not moving, the dislocations are not orienting, nothing is happening. All the things have already happened inside the material due to DDRX and CDRX. Now, during DDRX, the sedition which were given rise inside the material, now those are touching each other due to the geometric deformation, so much cross sectional reduction. So they are giving rise to new strain free grains. So this is GDRX. After that, the grain refinement will be taught in the next week lecture. So in grain refinement, we are having some new grains out of the old grain. So if the old grain was of this much size, now if the new grain is taking is give means forming inside the old grain, so obviously the new grain will have lesser size. So grain refinement has taken place. Refinement means giving rise to smaller grains. So this grain refinements also is dependent upon this Hall patch relation, which is a known, very well known relation for grain refinement. So the dislocation pile up and the stress develop at the pile up tip due to the Cottrell barrier and all those things were discussed. Only there were some formulas, nothing else. So you can go through the formulas. It's I think it's not that much complex thing to read. Uh, so if it's fine, we'll go to the MCQ section. So is it fine? If you have any doubt, you can ask. So I don't remember who asked me the question, Sanjit or anyone else, but someone asked me about the H321 heat treatment process. That what does those three letters
Ma'am,
do?
actually, like he's not right now in the meeting.
Okay, okay. Someone asked me, so I have got one website in which the alloy designations are present there. So, okay, no worry. I'll attach the link of those respective website in this slide, which will be shared to you later on. Okay, let's go to the MCQ section then. So try to answer the MCQ. We'll see the answers then. Reappearance of ill point will be much earlier if the material is allowed to age at. This is the current semester assignment for week 3 which you have already attended. I'm just discussing the answer for your reference.
Temperature more than the room temperature.
So, yes. Which of the following is are associated with dynamic strain aging?
PLC effect.
Any
Salinity. to sedative flow and solute atmosphere also.
Yes, three options are correct. All the things are related to dynamic strain aging, na? Because for dynamic strain aging, the solute atmosphere was built up, and due to that, the dislocation movement was hindered. And sedative flow and PLC both are the same thing. So those were present inside that. And due to dynamic strain aging, as I told you, you can see visually in your naked eye, you can see the serrated lines, serration lines in the alloy after some tensile test or after some externally applied load in the material. So serrated flow in the aluminum alloys occur at a strain rate of, at room temperature it's given.
10 to the power minus 2 per second to 10 to the power minus 5 per second.
Next is serration types change from A to B to C with, anyone? Any guess?
Um, is it increasing temperature and decreasing strain rate?
The strain aging process in terms of movement of solute atoms varies with time t as strain aging process.
No, is it t power minus 1 by 3? I'm not sure. It's the formula I remember. Okay.
Yes, T power 1 by 3. T power only 1 by 3. The alloying element is mainly responsible for yield point phenomena in aluminum alloy. Which one? It's easy.
Nitrogen.
No. Nitrogen and carbon are the alloying element for steel, which give rise to this type of
Magnesium.
component, magnesium.
Magnesium.
For aluminum alloys, it's magnesium. Carbon, nitrogen are from for steel. The atomic jumps are more often along.
Along the direction of the decreasing interaction energy.
Yes. The onset strain at which serrated flow starts will appear early if
Temperature increases and dislocation velocity decreases.
yes, serrated flow in the aluminum alloys can be avoided by, it's important,
You can avoid that range of strain and temperature in which solution occurs, like C option.
yes, testing the material by avoiding the range of temperature and strain rate where serration can occur. Difference between the maximum and minimum stress during serrated flow will decrease with
Increasing temperature, decreasing strain rate.
it's decreasing solid concentration, decreasing valency concentration, decreasing temperature, and increasing strain rate. So it's the current semester assignment for week 4, which you have already attended. So the first question was, when precipitates shear out by dislocation, then strengthening due to an increase in surface energy is.
Option C.
It's directly proportional to the volume fraction of the precipitate. It's directly proportional to the precipitate or particle matrix surface energy. C and A. When the aluminum alloy aged beyond the peak aging time, then what will happen? What is it called?
Theta phase.
Overaging.
It's called overaging. It's theta phase for 2000 alloys, no? For 6,000, 7,000, 8,000, those are differently designated, like eta, beta, gamma. So it's called the overaging. So what will be the answer?
Strength and hardness decrease, ductility increases.
And interparticle distance. Yeah.
Yes, interparticle distance or spacing also increases.
Ma'am, I had a doubt about coherency. Like, the coherency of this thing will decrease, or like it doesn't matter at this point.
uh, I will not say will doesn't matter, but it's like uh, the motive was to get an equilibrium position, and due to which they were trying to maintain the coherency. They will try to reduce the miscoherency. So when the equilibrium was achieved, na the coherency was lost. So at this point, the coherency cannot be reverted back, the coherency cannot be achieved again. So they do not bother about the coherency at all. So this is why we don't deal with the coherency anymore.
Ma'am, at this time, the precipitates form up like a lattice structure sort of a thing, which is a little different from the original lattice structure, is it?
Yes, yes. So the
Okay.
precipitates, like the accumulation of the solute atoms, but the accumulations, like, obviously they will be get bonded to each other, and if they are getting bonded with each other, means they are forming some unit cell or lattice, which is very much different from the parent lattice.
Is there any selection, like, say, if the parent lattice is FCC, then the
No, no,
precipitate has to be something?
no. It depends upon
Okay.
which parent lattice and which solute atom is present, how they
Okay,
are
ma'am.
bonding with each other, how much bonding energy they are having, how much attraction they are having with each other. In that way, they will get arranged in a particular lattice. But it's definite for
Understood.
a definite type of alloy element. Next question is, what are the necessary conditions for precipitates to form in an alloy?
Option D.
A as well.
Option A
And D.
and C and D. Solute atoms should have some solubility in the parent metal at room temperature, obviously, but it should have more solubility at elevated temperature, Solubility of solute atoms should increase with increasing temperature. It's like same thing, but different options. Okay. Small amounts of lead and bismuth are usually added in 6000 series. Why?
To increase machinability and reduce quench sensitivity.
It's increase the machinability. Quench sensitivity was due to something else. Now I don't remember. But 6000. Let me check for 6000.
Not too sure, ma'am, but is it chromium or something?
Chromium is always for grain growth or refinement,
Okay, yeah,
fine
yeah, you
refinement.
said that last class.
Uh, yeah, the quench sensitivity is low due to all the alloying elements, you can say, like not only for lead and bismuth. These two are typically adding some machinability, more machinability, but quench sensitivity is low because of all the alloying elements. Next is increase in strength due to coherency. Strain of precipitates and matrix will be related to misfit strength as
E got 3 by 2.
what what does the T651 temper aluminum alloy refer to? It's easy. I have already discussed this type of question in previous year assignment as well. No answer?
C. Uh, Solution treatment, artificial agent, stress relief and structure.
By stretching. By stretching से क्या करते? अच्छा लिखा ही है टेंशन और या ओके स्ट्रेचिंग से कौन सा स्ट्रेस रिलीव करते हैं टेंशन और कंप्रेशन
Tension.
नहीं
पर now tension, मतलब वो atoms will want to come back to their original position if you stretch it. So, like, it's like a tension inside the lattice.
हाँ but we are applying some tensile force but actually we are relieving the compressive force
Yeah, that. Oh yes, that is being relieved, and
yes
but like creating some tension. Okay,
हाँ
got
so
it.
to क्या बोलते हैं उसको to balance the minus we are giving some plus or to balance the
Yeah.
plus we are giving some minus so that it will be zero at the end
Yes, ma'am.
like
Understood.
that. So which of the following mechanism is are responsible for strengthening due to precipitations?
And I guess all of them except the B one. B.
So it's coherency strain between matrix and precipitates, change in interfacial energy due to particle shearing, local change in the modulus due to different particles. Strengthening of T4 treated aluminum alloys is mainly due to the formation of T4 means natural aging and not the peak hardness.
GP zones, solute clusters, stacking faults, and antiphase. Why not stacking fluid and antiphase?
It's T4, which is more natural aging. It should be stacking fault and antiphase boundaries as well. Mm,
Like I
let
remember,
me just see. I
I
guess for natural aging, the GP zone formation dominates. For
yeah,
artificial, yes, for artificial aging, it's different. It's the direct formation and with more time. But for natural aging, or sorry, for less time, the more temperature things for artificial aging. But for natural aging, this GP zone formation dominates. Maybe due to that, the stacking fault and antiphase boundary is not that much important for the natural aging part.
okay, ma'am.
As slow cooling from a single phase region in an age hardenable alloy will result in slow cooling.
Coarse particles.
So always for fast cooling, like quenching, it's fine particles. For slow cooling, it's coarse particle. So we have already now we have already the idea about the recrystallization where the nucleation and growth is taking place. So it's like for slow cooling, the temperature is high for longer time, so it gets more time to grow. The nucleated those grains get more time to grow. So this is why the particles are coarse in nature. But for fast cooling, as soon as you cool it down, you quench it down from very elevated temperature, very high temperature. In that case, they do not get enough time or sufficient time to get that growth. So this is why they are fine particles and strengthen due to the fine particles. So which of the following statement is are correct about GP2 zones in 2000 series aluminum alloy, which is theta double prime?
Option B is correct, man.
I guess the last and the second last as well.
So the GP zones are alternate layers of Cu and aluminum atoms on 100 planes. GP zones are larger than GP1 zones, but their number density is lesser than GP1 zones. Obviously, they are growing. And GP2 zones have disc-like shape, tetragonal crystal structures. Now it's about the previous year assignment that you do not have the access to. So this was the week 6, I think. So it's written week 5. It's the week 6 assignment. So annealing involves what? Recovery, recrystallization, grain growth, dislocation and entanglement, dislocation annihilation, strain hardening. Which of the following is are correct?
I think A, B, C, and D.
So it's obviously the recovery and recrystallization, and after that the grain growth will take place and the dislocation annihilation is take place. The size of the recrystallized grain is affected by
The temperature of recrystallization process, the degree of prior cold work, and stacking fault energy.
It's the degree of prior cold work and the temperature of the recrystallization process. Stacking fault energy you cannot say, because at some time you need more stacking fault energy, at some time you need lesser stacking fault energy. And for more stacking fault energy, the recovery will take place. For low stacking fault, the DDRX, the high stacking fault, the CDRX. So anyhow it's going to affect, anyhow it's going to take place. Anyhow, the dislocation movement is going to take place either by high or by low. Either it's hindered or it's getting some new arrangement, some high angle entanglement. So this is why stacking fault energy is is one important parameter that have some what say influence over the recrystallization. But anyhow, for low stacking fault or higher stacking fault, you are going to get new strain free grains, right?
Yeah, ma'am, understood.
So yes, stacking fault energy is an important parameter, but not in every case. Like degree of prior cold working is important, temperature of recrystallization is important, but stacking fault energy है तो अच्छा, नहीं है तो भी ठीक है. Next is assertionism type. So during recovery, dislocations arrange themselves in a form of an array. The reason is the energy per dislocation decreases as the dislocation are stacked and as an array. So which one of these are correct?
I guess both the session and reason are correct, and it justifies, like the session, reason justifies it.
So both A and R is correct and A justifies it. So the next question is, if you continue to extend the recrystallization process beyond the required time duration, what may happen?
Secondary recrystallization will occur and electrical conductivity will decrease.
Secondary recrystallization will occur. Electrical conductivity increases because the resistance decreases at the time of recrystallization. But you cannot say that as the secondary recrystallization is happening, some abnormal grain growth is happening, so electrical conductivity will anyhow decrease. It may get increased.
Mom, I didn't get you. Like, I don't
Okay,
understand.
so for normal recrystallization, which was happening for a particular recrystallization time duration, the resistance was decreasing, na? The conductivity.
Yeah.
So just for an example, you just take you just assume the resistance is increasing, conductivity is decreasing. So it doesn't mean that if you continue doing the recrystallization and if some abnormal grain growth is taking place, the resistivity will again increase. It's not the same graph. It's like overaging is taking place, but sometimes we also go for overaging. It's same similar thing na for secondary recrystallization, but it doesn't mean that yes, for overaging, how can I it's like secondary recrystallization will occur, abnormal grain growth will occur, the grain will grow beyond certain size, but you cannot comment on the electrical conductivity. It may get increased or it can happen like the conductivity this secondary growth is no anyhow not affecting the conductivity. The conductivity is at its upmost point, is having the highest conductivity, and it will remain at that point. It may get decreased, it may get increased, or it will may not have any changes, but you cannot comment on that.
Okay.
Okay, but because this electrical conductivity is not like dislocation movement. This electrical conductivity is something related to the electron and atomic movement, the electron movement inside the atoms. So it's not like, it's not dependent upon the dislocation movement. To some extent it's dependent. This is why for discrystallization, for new grains, for new strain free grains, the electrical conductivity was increased. But you cannot directly comment on the relation between electrical conductivity and the dislocation. To find out the exact relationship, if you want to know, then I will see if I get any reference in which you can get a particular relationship between electrical conductivity and the dislocation. I'll find. If I get, I'll share it
Sure.
with you.
Thank you.
So, which of the following is inversely related to the stacking fault energy? There are five options. There are four options, so this is misplaced somehow. Four options.
Starting point with the ease of cross slip.
It's like inversely proportional to the stacking fault energy. If the stacking fault
Yeah,
energy is high, means cross slip will move easily, na?
yeah, ma'am, I understood.
Regardless of the continuous dynamic recrystallization. Because for that we need low stacking fault to occur for high DDRX.
Yeah,
So again, there is a assertion and reason type question. So the assertion is grain with more than 6 phases or sides are less stable and tend to transform into triangular shape. Reason is the change in the shape from grain is driven by the minimization of surface energy. Which one? It's easy.
I guess both assertion and reason are correct. Uh,
How the assertion is
No,
correct?
ma'am, assertion is wrong because grains means grains with more than six faces they will tend to grow more rather than transforming.
Yes.
yeah,
So the triangular grains will tend to get demolished all in all time every time, and six phase or more than that grains will always try to expand there. But this change in shape of the grains is driven by the minimization of surface energy. So to get more surface energy, high surface area, they will always try to expand or grow. Which of the following is are not correct? Uh, Not the nucleation mechanism for a trace free grain or strain free grain. The correct answer is severe plastic deformation. Okay, why it's going so slow? I am in the previous slide only. Okay, so the answer is severe plastic deformation and annealing twins. So, due to the nucleation mechanism, the Zener-Hall equation, the result was the twins, and severe plastic deformation is giving us that scope for nucleation for the grain to get formed, the new strain V grains. But nucleation is not happening really because of the plastic deformation. Is it okay, this question for two of you?
Yes, ma'am.
Okay. The next question is it's a big question. Choose the incorrect statement. So the statements are minimum amount of cold work is needed for the recrystallization process, higher annealing time increase the recrystallization temperature, a higher degree of cold working implies a decrease in the temperature required for crystallization. Higher the recrystallization temperature, higher is the size of the recrystallized grain. Alloying increases the recrystallization temperature. What will be the answer? What do you think?
I guess fourth is not right, and so is the fifth.
The answer is only two incorrect because annealing time increases the crystallization temperature. No, annealing.
Yeah, that's the one, but also the fourth one. The size of the pre-crystallized grain should depend upon the holding time. No?
Higher the recrystallization temperature, higher is the size of the grain, recrystallized grain. It's like we cannot comment on that because temperature, if we are increasing the temperature, uh, it may happen that CDRS is happening. CDRS will happen in the at the time of deformation only, but like CDRS, the micro shear bands and all that may happen at higher temperature. At that time, the size will be lower. Refinement will take place.
Also, the alloy, like,
Alloying
is it
again, we cannot comment on the alloying increase the recrystallization temperature. It's not
okay?
right, it's not incorrect, but we cannot comment on that.
Yeah,
It affects, obviously, it affects the alloying solute, not the alloying, but yeah, because of the alloying, we are getting the solute atoms and the precipitates. So those precipitates affect the recrystallization temperature and time, but you cannot directly comment like if you are increasing the alloying elements, the recrystallization is increasing because you could have seen that in all among all the alloying all the alloying elements don't form the precipitates. In case of 6000 series, only Mg and Si were making the precipitates. For Li, for zinc, for 8000 series, the Li was making the precipitates. Although the main alloying element is making the precipitates, but there are other alloying elements also present inside the material, na? And they are not with very minimum amount. They are also with a comparable percentage. But yeah,
Yeah.
so yeah. Next is, it's the last question, I think. It's 10 number question. A block of aluminium is subjected to forging. You are cutting a piece of it and examining it with using DSC. Which of the following is are expected in the DSC plot?
I think exothermic peak during
Hmm.
recrystallization.
So the exothermic peak representing recovery, the exothermic peak representing the recrystallization. It's up to that. Okay, there is one another question. Choose the correctly matched pairs regarding the Zeller-Hallman parameter. It's easy.
High Z is twin boundaries and low Z is subplane boundary.
Okay. Low Z means twin boundaries and high Z means subgrade boundaries. But the dislocations will not.
Yeah, yeah. Swap.
Hmm. Okay, it's up to that. Thank you. If you have any further doubt, you can ask me. Otherwise, we'll stop our session here.
Ma'am, like you are from mechanical background.
Yes.
Okay. Well, like I thought that this is metallurgy class, so that's.
Okay, so I am a TA of this particular course.
Oh, okay, okay.
So, any problem or anything you want to say?
No, no, ma'am. I just saw that your mail ID, na, that mech.iitd was written. So I got curious that like
Yes,
how
yes,
mechanical person is teaching metallurgy. That's why.
yes. I'm a direct PhD student at IIT Delhi. Currently, I am in my third semester. My BTech was in mechanical, and my PhD is also in mechanical.
Okay, ma'am.
Okay, so yeah, if it's done, we can stop our session here.
Thank you.